So for the do now, this question is reviewing delta G, delta H, and delta S. So number one is having us look at essentially what they give us at the top to talk about delta G. And number two, we're actually calculating delta G and answering some questions. And then we're talking about the driving force of the reaction. So for number one, predict the direction in which delta G for this reaction changes with increasing temperature. So remember, when a question is asking you about how delta G changes with temperature, write out this equation. Delta G equals delta H minus T times delta S. Because when you are relating free energy, which is delta G, to temperature, you have to look at this equation, which means we need information about delta H and we need information about delta S. So if we come back up to the top here and we just try to figure out, we don't need the actual numbers, we just need to know the signs. So if we come back up to the top, it says the exothermic Haber process for the production of ammonia. Exothermic means, what is our sign of delta H? Negative. Delta H tells us whether a reaction is exothermic or endothermic. If it's exothermic, delta H is negative. So there's our sign of delta H. Delta S is determined from the balanced equation. So if we're looking at delta S, look at your reactants to products. Look at the states of matter. What's happening from the reactants to the products that would affect delta S. So the reactants, I have 4 moles of gas. The products, I have only 2 moles of gas. So because we're going from 4 moles of gas down to 2 moles of gas, that's becoming more ordered. And so delta S is also negative. So this is an exothermic process resulting in more order. So now that we know the signs, I know that this is negative. I know that delta S is negative. When I have multiple negatives, I like to manipulate this so negative times a negative is a positive. So I like rewriting this so I can say delta G is negative delta H plus T times delta S, because negative T times negative delta S results in plus T times delta S. So this is the equation now that we can focus on as we look at temperature. We are focusing on increasing temperature. So this value of T is getting larger and larger and larger and larger. Eventually, this T times delta S quantity is going to be larger than delta H. And when T times delta S becomes larger than delta H, what's going to happen to our sign of delta G? It's going to be positive. So predict the direction. We can say eventually delta G will be positive. And our reasoning, like we saw yesterday, our reasoning can be focusing on this and saying eventually T times delta S will be greater, resulting in a positive delta G. And then number 2 says, use Appendix C to calculate delta G of the reaction. And then it's asking about thermodynamic favorability. So if we are looking at delta G, Appendix C is the coral colored stapled papers. And so remember, Appendix C has delta H of formation, delta G of formation, and S. Here is our balanced equation. Because it says use Appendix C, we're going to be using this equation. Delta G of reaction is the sum of the free energy of formation of products minus the sum of the free energy of formation of reactants. So if we take a look at Appendix C, We're solving for delta G of reaction. Products, ammonia. NH3 will be under nitrogen. So if we flip to nitrogen in Appendix C, make sure you're looking at delta G of formation. And notice there's two NH3s. There's aqueous and there's gas. We're looking at gas. So NH3 gas has a delta G of formation of negative 16.66 kilojoules per mole. Remember, you have to take into account coefficients. So 2 times ammonia, there's our products, minus reactants. I'm not even going to look at my reactants on here. Why do I not even need to look at reactants for both of these? They're 0. These are the elements, right? These are diatomic elements, so molecules, that are in their most stable state. N2 exists as N2 gas. Hydrogen exists as H2 gas. They're both 0. So really, we have 2 times the free energy of formation of ammonia. 2 times negative 16.66. Would I have done this without a calculator? Probably. Negative 33.32 kilojoules. That's number 2. I'm just trying to do it in some free space. So then it says, is the reaction thermodynamically favored at 25 degrees Celsius? Why or why not? Remember that this little not symbol means standard conditions. 25 degrees Celsius is standard conditions. So we can just look at our value of delta G. Is this thermodynamically favored? Is it spontaneous? Yes. Yes, because delta G is negative. If delta G is negative, it is thermodynamically favored. Spontaneous, it happens on its own. Assume. So then number 3, what is the driving force of this reaction? Delta H or delta S? Now it's not having us explain, it's just having us answer the question. So we know that this is spontaneous. Delta G tells us that the reaction is spontaneous. But if we take a look at delta H and delta S, delta H is exothermic, delta S is becoming more ordered. Well, which one of those conditions, if any, does nature favor? Exothermic. Nature wants exothermic and disorder. So whichever of those we have, sometimes we have both. But whichever of those we have, that is what the driving force of the reaction will be. So for number 3, delta H is the driving force. And what that means, if we look at this equation, is that delta H is larger than T delta S, which is why delta G is negative. Right? It's more negative than that T delta S value. Questions on the do now? So if not, you can go ahead and get out your notes. You will still want Appendix C, and you'll want a calculator. So notes, Appendix C, and calculator. We're going to go through one example, one practice question, and then we'll actually work on the lab a little bit. So we'll set up calculations and work through the lab. So while you guys are getting out your notes, I want to just talk a little bit. There weren't very many questions on the video, but I do want to just cover some of the key concepts and talk just for a second about what is not tested anymore. So connecting free energy, which is delta G, to equilibrium. If we have delta G on your equation sheet, you have an equation that is delta G equals negative RT ln K. You have an equation. This equation right here is on your equation sheet. Now, this equation is just the rearrangement of this one. Because E, right, that's how we can get rid of a natural log. So this K equals E to the negative delta G over RT. That's just a manipulation of this equation. This is on your equation sheet. If we have delta G, we can solve for K. If we have K, we can solve for delta G. Now, when we think about free energy, about delta G and K, when something is thermodynamically favored, spontaneous, that means it happens on its own and products are favored. Remember, going back to equilibrium, products are favored when K is greater than 1, because your equilibrium expression is products over reactants. And so when something happens on its own, reactants convert to products. Products are favored. If it is not spontaneous, so delta G is positive, we would say reactants are favored, because the reaction doesn't happen on its own. So we have reactants. More reactants than products. If delta G is near 0, so if delta G is close to 0, that means that we are close to equilibrium. Remember that delta G is 0 when we are at equilibrium. So if delta G is 0, K is 1. So it just allows us to relate a spontaneous or the favorability of a reaction to the equilibrium constant. There are no longer questions on Q. So in the video, I talked a little bit about Q. They don't test on Q with delta G anymore. They test on Q with just equilibrium, but they no longer tie it into delta G. This information, this is all that they test on relating delta G to equilibrium. So you're given a delta G, you need to solve for K, or the other way around. And so what we're going to actually do is we're going to look at example 14. So in your notes, you have examples 12 and 13 as well. We are skipping them. If you want to put a big X through 12 and 13, go for it. But 12 and 13 related to Q. And that's no longer tested, so we're skipping them. Example 14, though, is definitely a question that we could see. Now, obviously, instead of using Appendix C, they would give us values to use, but this will let us practice using Appendix C a little bit more. So example 14 says, use data from Appendix C to calculate Kp at 298 for the following reaction. So let's say this is a test question. They would not have you rely on Appendix C. They would give you values. The values that they would give you would be the free energy of formation. So if we look at the equation sheet first, I notice on the equation sheet, I have the equation delta G equals negative R times T times ln K. My goal is to solve for K. This K could be any K, KC, KP, KSP, KQ, right? This could be any K, but this is what I'm trying to solve for. Before I can solve for the equilibrium constant, I need to know delta G of this reaction. This is why it says use Appendix C. So here's my balanced equation. The first thing I need to solve for is delta G of the overall reaction. Another equation on your equation sheet is the sum of the free energy of formations of products minus the sum of the free energy of formation of reactants. So we look at Appendix C. We know that we need to do 2 times the free energy of formation of HI. So HI will be under iodine. Iodine it is. And delta GF, that's the center column. 1.30 kilojoules per mole. minus the free energy of formation of the reactants. Now be careful with this one. Right, be careful with this, because yes, H2 is in its most stable state. That's 0. I2 gas is not iodine's most stable form. Iodine exists at standard conditions as a solid. So if you actually look at Appendix C, you notice that iodine gas has a free energy of formation of 19.37. So be careful with your equations. Again, if this were a free response question, they would give you the free energy of formations, or at least of I2 and of HI. It might not give it to you for H2, because then you have to know that that's in its most stable form. So by multiplying by the coefficients, that cancels out the per mole part of the unit. So 2.6 minus 19.37. The delta G of reaction, so the free energy of reaction, is negative 16.77. Of course, we have to have one part of this unit where units can be tricky. We had it with entropy, but now we also have to pay attention when we're looking at the equilibrium constant equation. This is kilojoules. Delta G of reaction is given in kilojoules. So now we have a delta G that we can plug in. I'm going to rearrange this equation before I plug in numbers, because I don't want the numbers to hinder us rearranging this equation. My goal is to solve for K. And I know this was in your notes, but I want to show you how to solve for this, because this is the equation that is on your equation sheet. So if you're, in the middle of the AP test, you want to be able to manipulate this fairly quickly. So the first thing, I'm going to divide negative RT over to the other side. I'm going to divide RT over. So I'm going to get negative delta G over RT equals ln K. Natural log of K is one variable right now. You can't just divide by ln. Your calculator is going to say, sorry, that's not right. To get rid of a natural log, you can do e to the x. So e to the ln K allows me to just have K on one side. And then e to the negative delta G over RT on the other side. Now, when we plug in values, I'm going to write them all out. So here's my delta G already. If we're looking at R, we've looked at R before. That's the ideal gas law constant. All of your values of R can be found on the equation sheet. You have 3 different values of R given on the equation sheet. Because we're dealing with energy, we're going to use what I call the energy R. The energy R is 8.314 joules per mole times Kelvin. And then T is temperature. Well, if you look at your units for R, it needs to be in Kelvin, which we've been looking at. They gave us temperature in Kelvin already. Now, if you take a look at these 3 variables, what do you notice? Right, delta G is in kilojoules. R is in joules. Whichever you convert is up to you. It's up to you on whichever one you convert. I see people convert both ways. Whether you convert delta G or whether you convert R, that's up to you. I'll convert delta G for now. Remember that 1 kilojoule is 1,000 joules. Obviously, if you have kilojoules that are already in the thousands, multiplying by 1,000 will give you a really large number. If you convert R, you would divide by 1,000. So this would give me negative 16,770 joules. Check your units. Writing out the variables like this is useful because you can check your units. Once all of your units are the same, now we can plug in. K, that's the equilibrium constant. They told us here they wanted Kp, so we're just going to label it Kp. Negative delta G, that negative is part of the equation. My delta G is negative 16,770 divided by the quantity R times T. Oh, I forgot my E. Oh, jeez. E to the negative delta G over RT. So it's R times T on the bottom. So when you plug this into your calculator, I like working backwards, and especially because I'm using a graphing calculator anyways, I can just go back up and hit answer and have it put it in. So the first thing that I would do, I notice I have negative and negative. Well, those negatives are going to change to a positive. So I have 16,770 divided by, and 8.314 times 298. $2,477.52. Now, could you do it all at once in your calculator? Sure, you just have to be careful. So I can do 16,770 divided by this answer, and I can do E to that value. Remember, E is second ln. In your calculator, E is second ln. So in my calculator, I would say second ln, and put this in parentheses. I got 870. So just make sure that you can plug things like this into your calculator. But this is how, if you have delta G, you can actually solve for K. So a large K means that products are favored. Going back to equilibrium a little bit, a large K means products are favored, which is also true because this is a spontaneous, a thermodynamically favorable reaction, which means reactants convert to products. So it allows us to kind of tie back in equilibrium. Questions on example 14? Yeah.
I'm looking at the units. Joules cancel and column cancels. What mole?
So because we have moles here, technically this is kilojoules per mole of reaction. And so if we do per mole of reaction and we have per mole here, those will cancel out. We usually will just stick with like joules or kilojoules because the per mole of reaction sometimes trips people up. But yeah, technically we would have per mole of reaction here, and so then those would cancel. Yep. Other questions? So I'm going to actually have you guys work in a small group again like we did yesterday, where we're going to do the last practice question. So the last practice question is practice question number 9. This is on page 15. Somehow the second half of the practice question got cut off, and I'm not sure how, like in your guys' notes. So I have the entire question up here. You guys in your notes just have A and B. And I was looking at this morning, like, where's the equilibrium part in the notes? So somehow it got cut out. But I'm going to leave this up here so you guys can answer C and D as well. You'll just have to read through C and D up here. So you'll go through answer A through D. So you're thinking about delta H, delta S. It's going to kind of go back and review some things about delta H and what it means about breaking bonds. And then part B is actually having you tie something into a graph. And then C and D are having you focus on the equilibrium part. So work with a partner, small group, talk to each other. I'm going to give you guys about 9 minutes. So work through this. Use your equation sheet, calculator, right, and try to answer these questions. As we go through the answers for this practice question, you can tell that this is a practice for your response question just from the way that it's worded. Everything says justify your answer or explain. And so you'll be able to see not only the answer, but how they scored this question as well. So for part A, and I have each answer on a different slide just to make it easier for us to see. So it says that the gas N2O4 decomposes to form the gas NO2. So it tells us that both of these are gases, but then it allows us to actually see at the molecular level what it looks like. It shows us the Lewis structures. So part 1 says predict the sign of delta H and justify your answer. Now it doesn't tell us whether it's exothermic or endothermic in the problem, but what they show us is the Lewis structures for each one. Notice to get from N2O4 to 2 NO2 molecules, this bond has to be broken. And when we talked about thermochem, we talked about bonds breaking and bonds forming. Think about a bond like a ruler or like a stick. If you want to break it, you have to put energy in. You need to put energy into the bond to break it. So that's endothermic. So bonds are broken when NO2 molecules form from N2O4. Since energy has to be absorbed to break bonds, it's endothermic. Delta H is positive. So notice it said to predict the sign. So you should have said delta H was positive. That was just 1 point for the sign and the explanation. So you had to talk about breaking a bond. Breaking a bond is endothermic. And then predict the sign of delta S and justify your answer. We are going from 1 gas to 2 moles of gases. So since we are creating more gas, that means we're creating more entropy. And so delta S is positive. Again, that was 1 point for the correct sign and correct explanation. Remember to tie entropy to states of matter. They want you to tie it to states of matter now and not just say more disorder. If you think about disorder in your head, that's fine, but when you're justifying, relate it to states of matter. Part B, one of the diagrams below best represents the relationship between delta G and temperature. Assume that delta H and delta S are independent, so that means that the signs of the two remain the same. Draw a circle around the correct graph and explain why you chose that graph in terms of the relationship. Delta S was positive. Delta S was a positive number. So as temperature increases, T delta S becomes larger. And so you are subtracting a larger number from delta H. Eventually, delta G will get smaller and smaller and smaller and become negative. Right, delta G gets smaller with increasing temperature. That was 2 points, 1 point for choosing the right graph and 1 point for explaining. So because as temperature increases, delta G is getting smaller. Eventually it would cross the x-axis to become negative. That's why that first graph is the best answer. So C and D, this is what did not get added to the notes, but it's what tied in equilibrium. So it was the part that went with what we were doing today. So for part C, the reaction mixture of N2O4 and NO2 is at equilibrium. Heat is added while it's maintained at a constant pressure. Part 1, explain why N2O4 decreases. So if you needed to, you could write out the equation. N2O4 is at equilibrium with 2NO2. Well, the reaction is endothermic. For endothermic reactions, that's like heat acting as a reactant. So when you increase the temperature, you're going to have the forward reaction occurring. Right? You're pushing the reaction to the right. And so this increases the concentration of NO2 and decreases the concentration of N2O4. That was just 1 point. And then part 2, the value of KEQ. So the equilibrium constant is 5 times 10 to the negative third. So 5 times 10 to the negative third. That means that it's less than 1, so reactants are favored. Will the value of KEQ at 100 degrees Celsius be greater than, less than, or equal to this value? And so it related it to the reaction being endothermic. At higher temperatures, reaction goes further to the right. Delta G is becoming more, it's becoming smaller, eventually would become more negative. So as delta G gets smaller and eventually becomes a negative for a spontaneous reaction, K increases. So the value of K at 100 degrees Celsius will be greater than the value of KEQ at 25 degrees. So notice how it actually just says 1 point for the correct choice. It doesn't say you had to explain. So you had to say the value of K will be greater at 100 degrees. And then finally, part D, using the value of K at 25 degrees Celsius, given in part 2 of C, predict whether the value of delta H is expected to be greater than, less than, or equal to the value of T delta S, and explain. So this shows, based on what they give us here, that we need to use that equation, delta G equals delta H minus T delta S. And it says explain, so make sure to explain. So since K is less than 1, delta G is positive. Since reactants are favored, delta G is positive. It's not thermodynamically favored. So for delta G to be positive, delta H must be greater than T times delta S. So your explanation, all right, you needed to somehow talk about delta G being positive, but it was 2 points. 1 point for saying that delta H is greater, 1 point for the explanation. So notice how sometimes it's just 1 point for having both, or it's 1 point for each individually. But these practice questions, all 9 of these practice questions were old AP questions, whether multiple choice or whether free response. So just good practice. Any questions on the practice?